All right, so thanks for the opportunity to talk today. So my name is Julian Mak. I'm currently an assistant professor at HKUST in the Department of Ocean Sciences, actually. So normally I get lumped in together with the physical oceanographers. So I generally don't regard myself as a physical oceanographer. So I happen to do a lot of kind of fluid dynamics research in the context of physical oceanography and as opposed to the climate. But the kind of things I really do is, I guess, I try and understand how things flow. My main interest really is on things like instability and waves. So how does the mean flow generate instabilities and waves, and how do these things interact to feed back onto the mean state? So I gather most of you don't have that much exposure to general fluid dynamics. So I thought the thing I'll try and do today, just to give you a quick introduction, a very broad overview of the kind of things that can kind of go on in fluid dynamics research. Focusing probably in particular on topics which are fairly classical. There's nothing fairly fancy about these topics. But the thing I will do is probably put in a way that you may not have been familiar with or not seen it put that way before. Okay, so just a bit of background about myself, just to give you a bit of context on the kind of things I'll be talking about. So I did an undergraduate in maths and a postgraduate in maths. So traditionally in the UK, if you're doing theoretical fluid dynamics, you're usually lumped into applied maths department. So that's where I was. So my background is really in magnetic hydrodynamics. So I've been looking, so during my PhD, I've been looking at a lot of work to do with shear instabilities within the context of motivated by the solar interior. So here we have things like rotation stratification as well as the influence of magnetic field. So after that, when I went for postdocs, I gradually moved away from doing MHD stuff. So now I mostly do geophysical fluid dynamics. So focusing particularly on the ocean and the atmosphere. All right, I still in MHD, but not so much these days. All right, so let's maybe talk a little bit about the fluid dynamics. So a lot of things I do actually is to do with computation. So I didn't make this, but this is something that in principle I could make. So I can't know how you make it. So it turns out in this case, I think you just make a mesh and a dinosaur, and then you can put this in OpenFlow and do it. That's not really what I'm talking about today. So I'm going to talk about some kind of more general fluid topics. Let's see, is this working? Yes, okay. There's a bit of a lag. All right, so just to put this in context, so this is a graph I took from XKCD. So this is a graph of standard, I suppose, physics topics. On the x-axis, you have how interesting, well, how technical things are, and on the y-axis, you have how interesting things are. So you have the standard topics like special relativity and quantum mechanics and general relativity down here. And fluid dynamics is normally put here. So I guess in this case, the author is thinking that it's a very technical subject, and in some ways it's not philosophically very interesting. In some sense, that's probably true. I'm not really defending against this. So fluid dynamics is actually quite a technical subject. It might not be philosophically interesting, but it is very aesthetically pleasing, I find, generally. So one of the things that particularly attracted me to fluid dynamics is the fact that you can make lots of movies. So if you just simulate the fluid dynamic equations, you can easily make very nice movies out of them. Another one more practical is that if you have kind of training in fluid dynamics, you can go into engineering, you can go into research engineering, hydrodynamics, environment stuff, even stock market stuff. So it turns out a lot of stock market people really like people who have some sort of training in PDEs. So that's what fluid dynamics really is. So part of my choice of choosing fluid dynamics is really for safety, it's just for job security. And another reason I guess I chose fluid dynamics is because I really like the technical stuff. So some people hate the technical stuff. I love that stuff. So one of the things which I'll be focusing somewhat on in the topics here in fluid dynamics are somewhat, so I think I'll mention some of the technical details. We'll go over really from an overview point of view. So I'm not going to go into technical details as such, but I'll mention them in passing. So some of the topics I've chosen today are, so I've chosen them particularly for the links with the mathematical theory, and as well as with other fields of research. It's generally true that not just in fluid dynamics, but generally in research, most of the easy stuff has been done already. So the remaining problems are either the really hard ones or the really ugly ones, and the really not interesting ones. So I'm not saying these are not important. I'm just saying that some of the ugly and uninteresting things are not necessary. They can be important. They're just really ugly and uninteresting sometimes. So the ways you can go about it is usually either you go and find a problem where you can try and either carve out a niche for yourself and try and exploit it as much as possible, or which is the kind of somewhat of the focus here, is you try and look at maybe more classical problems but in a slightly new kind of lens. So another kind of choice of the topics I've chosen here on the topics where it's really fairly classical, but I'm going to spin it in a slightly different way, all right? Particularly drawing links with some of the more familiar topics in physics, some of the techniques you might encounter in physics, all right? So that's kind of the plan of attack. So there's three parts of this talk. The first part is I'm just going to quickly talk about kind of broad fluid dynamics, talk about the fluid description, just give you some physical context as to where the fluid description can be applied to. I'm going to say a little bit about Navier-Stokes, the Navier-Stokes equation. So these are that's basically the underlying equation that governs fluid descriptions. So for time reasons, I've actually put in 3 reasons why the problem of Navier-Stokes, and by corollary, the problem of turbulence, why is it really hard? For time reasons, I'm only going to go through 1.5 of those, okay? So the upshot from the first part is that the fluid description, turbulence is really hard. It doesn't mean you just go cry and give up. So there are certain limits where you can actually do some stuff about, make some progress. So I'm going to focus on some fairly maybe classical but somewhat well understood examples in classical fluid dynamics, so particularly in aerodynamics. To do with and also swimmers. So I'm going to focus on the case where talk a little bit about the case where you have a really viscous flow and a case where you have an ideal flow, so where you have absolutely no viscosity whatsoever. The dynamical system stuff I'm going to skip because that's actually again mostly the time reasons. Okay. So usually when people say they give talks, so a third of the talk is maybe for everybody, a third of the talk is for specialists, and a third of the talk is for the speaker in some sense. So the third part is really for me. So I'm kind of using this as an opportunity to talk about stuff that I don't normally get to talk about. So it's some of the more theoretical stuff that I personally get involved with. So the 3 topics I'll try and touch on are the Hamiltonian fluid dynamics with a Hamiltonian description of fluid dynamics, topological protection, which is a fairly new thing, certainly in the classical sense, it's fairly new, and what's called PT-symmetric operators. So most of these are going to be applied to waves and instabilities. So for those of you who have some sort of background in condensed matter and quantum mechanics, you might know about topological protection and kind of non-Hermitian operators already. So I'm going to try and touch on those a little bit. All right. So there's kind of 3 reasons for the choice of topics I made. So there's many different things like I talked about. The topics I've chosen here are in fairly specific bias choices. One reason is to I suppose it's because they are interesting videos, interesting pictures, or stupid pictures I can show, or absurd scenarios. So I really like absurd stuff, so I'm going to try and focus on those a little bit. The second bit is these are fairly classical problems that you have a fairly good intuitive understanding of, but I'm going to try and spin it in a slightly different way. And the third is really a scientific reason. So there is a scientific reason why I chose this kind of the topics. Is really to do with the role of symmetries. So throughout most of the talks, I'm going to be trying to highlight the role of symmetries in conservation laws in describing these systems. So the upshot here, at some point, I'm going to start using Noether's theorem. Right? So when I get to, that will be explicit when I get to the non-canonical Hamiltonian stuff. So I'm not going to talk about the rheology of cats. You can ask me about that later on if you really want to. Okay, so let's make a move on then. Right. Equations. Okay, let's get the equation out of the way now. So generally, if you are normally what you do is so there's kind of 3 levels, I suppose, roughly 3 levels when you look at trying to describe a system. So one is you look at the particle point of view, so that's kind of the standard in the graduate way. In a more statistical mechanics way, you might say you have lots of little things and you want to say, what is the average kind of behavior? So you're still looking at it from a collection point of view. And then you can look at it from the continuum point of view, or from the kind of field theory point of view. So fluids is really in the latter case, where you consider things as a continuum. So the usual derivation is you take a collection of fluid parcels of particles. You assume that, so the fundamental assumption here is that there's a small mean free path. So particles don't travel very far before they bump into each other. For my case, I'm going to assume everything's Newtonian. So there's a linear relation between stress and strain. It's incompressible, so you can't squash the fluid. So what that's going to mean is I can essentially throw out thermodynamics. So I don't need to consider kind of evolution of internal energy and entropy and all that kind of stuff. The incompressible Navier-Stokes equation I'm going to be dealing with is this one. All right. So I've written it in a specific way. So here, this is the density. So this is the mass. This is really an acceleration. This is acceleration following fluid parcels. So it's like Eulerian type derivative. And this is really the forces. So you've got internal forces like pressure, something to do with viscosity, that's the resistance to air within body stresses, and you've got the external forces. So you put it this way, this is just momentum conservation. So it's just F equals ma. So F is on this side. And the bottom bit is mass conservation, but put in for incompressible flows. All right. So I'm going to stick with the vectorial form. So you could write this as from a tensor point of view. You can write this from a geometric point of view. You can write this in terms of like things like lead derivatives if you really wanted to. I'm not going to touch that here. All right. And the name of the game is that, so given all the forces, so given external forces and an initial condition, tell me what's going on later on. So I want the velocity and the density later on. Okay, so if you are rotating, you might want Coriolis effect, and if you are in the magnetic case, you might want the Lorentz force and so forth. All right. Okay, so that's the physical bit. Mathematically, what we have is a second-order nonlinear PDE, subject to a good strain. So it's second order because of the Laplacian term here. So mu here is going to be a coefficient of viscosity. It's nonlinear because of this guy. This is usually called the inertial term. So most of the annoying things or the interesting things come from this guy. So one thing I just quickly want to say is the fact that, so this kind of set of equations has a singular limit, a singular behavior. So what I mean here is that the equation behaves very differently when mu is 0 and mu is really small. They're not the same things. So in the case, so what I'm saying is that the solutions in the limit of mu tending to 0 is not the same as the solution of mu equal to 0. In the latter case, you're dealing with a first order PDE, and in the former case, it's a second order PDE. They have really different behaviors. So this is also going to be, so I'm going to show a case example of this later on. So this is subject to constraint. So it's this guy, so diff u equals 0. So this is like mass conservation. So what you really should think of this is, so this isn't really a pressure. You should think of this as like a Lagrange multiplier. So P is whatever it needs to be to keep the diff u equals 0 constraint. So for example, if you're dealing with numerical implementation of, say, the Maxwell equations, you could do something similar. So what you do is you introduce a Lagrange multiplier such that diff b equals 0 everywhere. Otherwise, you have maximum monopole and so forth. And what that usually means is you have an extra Poisson equation you need to solve. Okay, so that's the equation, and we get it out of the way. So the key point is going to be this one later on. So what we're going to do about this guy later on. All right. So really in the case here, so the main assumption about the fluid description is really to do with the small mean free path. And small here can mean a lot of different things. So it could mean that so small could be relative to the system's size. So sometimes even in the very large astrophysical scenarios, even you're dealing with dust, you think they're really far apart, but from a large scale point of view, they're not actually that far apart. So there's a high collision rate. Then you can use a descriptive fluid description for this. So the two astrophysical examples I've given here are to do an accretion disk. So here you have a center, you have a really massive object in the center. It could be a neutron star, it could be a black hole, it could just be a big star, it doesn't really matter. And you've got stuff which is going around this thing. So this is done through what's called SPH, the smooth particle hydrodynamics. Some of you might recognize this one. So people in the gravitational waves group here might recognize this one. This is from Patrick's paper. So this is a relativistic jet. So these are what's called the AGN jets. All right. So in these kind of scenarios, it depends. So it's ultimately underneath that there is some kind of semblance of the Navier-Stokes, but there is other things going on. So for these kind of things, you might want things like self-gravity, because you got these individually have some density, and the density changes if it's large enough. That might lead to a change in the gravitational field. Because of these kind of things, so here you probably want compressibility. You don't really want to assume this is incompressible. If you have compressibility, you want an evolution of thermodynamics as well. For really fast and really massive objects, or in some sense they're really the same things. You might want relativistic effects as well. So you can, so in this case, the evolution of the density, I suppose, would be coupled to some sort of evolution of the metric, if you're taking it from a general relativistic point of view. All right, so that's the kind of really large scale. If you're dealing with magnetized fluids, which you normally encounter things like stellar objects, or even in the kind of smaller objects, it's like, say, in fusion, then you want magnetic effects. So here what you have is you've got the fluid which is stirring up the motion, stirring up the magnetic, it carries around magnetic field lines a bit, so it's going to end up stretching and stirring the magnetic field lines. So via some sort of electromotive force, that's going to lead to some sort of evolution of the magnetic field. The magnetic field in turn gives you a Lorentz force, so the Lorentz force ends up feeding back on the fluid elements, and so there's some sort of coupling going on. So this would be in the domain of MHD. So here the two examples I've given are, these are both simulations. So this is quite a famous picture within the MHD community. So this is one of the first simulations of a geodynamo. So this is, so in the Earth there's a liquid core, a liquid metal core, so that ends up driving a dynamo. So you have a very strong dipolar pattern in the magnetic. So these are magnetic fields. This one is a simulation, I think it's a fluid description simulation of a tokamak. So a tokamak is like a standard configuration you use in fusion. So here you've got things like kinetic effects going on as well, presumably. For these kind of cases, you might want to distinguish protons and electrons. So you might want to have things like, you might want to be dealing with a whole MHD and so forth. All right. So this is the kind of thing that I focus on quite a lot, is on planetary bodies with a particular focus on the Earth. So I mostly deal with the ocean, but I also look at the atmosphere occasionally. In some sense, it doesn't really matter. They're kind of one and the same to me anyway. So here, these are the two examples I've given here. So this is the atmosphere of Jupiter. So this is from the recent Juno mission. So what they see is it's a false coloring on the clouds, which are seen on the weather layer of Jupiter. In the bottom, this is I guess this is the velocity, or it's not really velocity, it's the magnitude of the current speed inferred from what's called satellite altimetry. So these are observations, essentially. So the main point here is that, so both of these systems are rotating stratified systems. So certainly the thin top layer of the Jupiter is regarded as a fairly stratified region. In the ocean atmosphere, these are stratified, and it's certainly rotating. So what you have in both of these cases, you have some sort of kind of large-scale structure, which is to do with like a jet. So I don't know if you can see there's some sort of jet going on here. There's also small-scale fluctuations like the vortices. There's also waves, but I guess you can't really see the wave in this case. Similarly, in the ocean, you have that as well. You've got the what's called the western boundary current here. And these end up shredding off what's called mesoscale eddies in the ocean, and there are also waves in this case. Okay, so in some sense, actually, so they're fairly similar because the dynamical process generating these are actually fairly similar as well. So that most of these come from some sort of barotropic or baroclinic type instabilities. So that's kind of actually what my research bases in. So I mostly look at how the large scale generates the small scales, so through some sort of instability, and how these small scale interact and feedback with the large scales. So the kind of stuff I deal with is really multi-scale dynamics within the fluid context. Right. So the common features to do with small scale fluctuations, there's some sort of self-organization, and you want to somehow model these small scale fluctuations back onto the large scales. So these kind of things have implications for climates and so forth. In the more classical case, these kind of objects still exist. So here we have the classical examples of what's called from carbon vortex. So this would be a vortex which is shredded from a wing. You get these jets. So this is the Merlion in Singapore. So you're shooting out a jet through a pressure differential. This, I think, is convection in a soup. So this is what's called Rayleigh-Bénard type convection. And the common features a lot, with these kind of things, right? There's a jet, and then somehow there's some sort of bubbles going on, splutterings going on. So you want to know. So these come from things like instabilities. When you generate these things, you end up generating kind of circular, not circular, but rotating structures like vortices. How do these small-scale things end up feeding back into giving you some sort of large-scale kind of coherent structure, or there's some sort of self-organization going on? All right, so that's the kind of stuff which is generic in the fluid dynamics. You can go even smaller scale. On the left here, we have what's called dinoflagellates. So this is the kind of small things that are floating around in the ocean. So these are important for things like the marine ecosystem and the food web. And in turn, I guess, also for the carbon cycle. On the right-hand side, you've got, so one of the things we'll talk about later is how do these things actually swim? So we'll get onto this in a bit. Because the migration patterns of these things are actually kind of important. You want to know these from the climate point of view. And the microphysics in this case is actually very important. In the physiological cases, you're still really dealing with fluids. So blood flow, even though it's very tiny, you would still regard it as a fluid. Or you might have things like lung kind of flowing within the lungs. You might have extra kind of variations such as flow within an elastic wall, or things like porous media flows, but ultimately there is still a fluid description you can use here. So the bottom one is my last kind of context example. So this is a Bose-Einstein condensate. So what you see from quite old, I think this is from 2001 in science. So what you see is lots of these little dots. So these little dots are what's called topological vortices, or sometimes they're known as ensemble vortices. So these kind of things do arise even in the quantum case, and so you get some of the quantization going on. So there is some sort of similarity, even at the kind of very small scale level, where the fluid description might be useful. All right. So my kind of main point with this 20 minutes of stuff is really to say that the fluid description really, there's many different applications across multiple scales. So in some sense, I'm kind of surprised. In a way, I'm always surprised why these things are not really taught in kind of the physics department, because that's kind of the standard thing to go for. Right? There's one description ends up giving you multiple applications. But really, maybe another way to think about this is that ultimately, fluid turbulence and fluid interaction is really to do with a strongly interacting multi-scale nonlinear system. So the fact that you happen to be applying to fluids is kind of neither here nor there. Really is the multi-scale interaction part, which is important. All right, okay. So I'm going to give you a few. So this is kind of a promise bit about why the kind of Navier-Stokes, a few properties about Navier-Stokes equation and why the Navier-Stokes stuff is hard. So there's three of them. So it's mathematical, there's a statistical reason, and then there is the computation reason. So I'm going to skip the mathematical one. I'm just going to leave this out lying around. Just for time reasons. If only to say that in some ways, the upshot here is that we don't really know whether the Navier-Stokes in a way is actually a good model, or it's actually a well-defined model, because we have no constraint on whether the things blow up, or it's well-defined mathematically. It's one of the still open Clay Millennium Prize problems. So it was one of the 7, it's now one of the remaining 6. So the upshot here really is that the mathematical analysis of the Navier-Stokes equation is kind of hard. It's still a really ongoing project, ongoing problem. People have been looking at this for a long time. So probably since the time of the Ray, so this would be kind of early 19th and early 20th century. So just for the purpose of this talk, I'm going to just ignore this point. I'm just going to assume that, okay, it might not be mathematically well defined, but it's a useful description. Maybe we just use it as like ignoring the fact that there might be kind of fundamental reasons why this is a bad model. So let's assume, like, ignoring the mathematics part. So how might you try and get information out of these equations? So this one I'm going to be a bit skimpy on. It's to do with the statistical way of trying to describe these things. So what this is kind of inspired from statistical mechanics, I suppose, is so normally in a statistical mechanics formalism, you might say you got the microphysics of each particle. Describing them individually is very difficult. So how about you just take a coarse graining, average over some sort of microphysics to give you a description from macrophysics. So a similar approach is kind of done here. So this is related to what's called the closure problem. So what you want to do is you want to somehow split out a large scale and a small scale part, and you want to average out the small scale part and get a description of a large scale from the fluctuations or correlations of the small scales. In the climate count analogy, what you might be doing essentially is averaging the weather to get a description of the climate. So that's something you might kind of bear that analogy in mind. The problem is you can't do it essentially. So well, you can, but then so there's a so the upshot here is that if you do this for the Navier-Stokes problem, what you get, partly because of the non-linearity, what you get is that if you want a description of the lower order statistics, you need the first order statistic, you need the second order statistics, and you need the third order statistics, and you just keep going. There's an infinite hierarchy of correlations you need to get at. So the way you normally deal with this is you have to either close it in some way, or you have to model this in some sense or another. So you have to manually truncate this. So I'm going to leave this slide open again. So most of the approximations are not really mathematically kind of rigorous as such. So most of these are kind of fairly ad hoc, or they're justified by some sort of physical intuition. Depending on the context, some of them work okay, some of them really suck. So there are cases where you can get negative energy coming out. So if you assume it's Gaussian, for example, you get negative energies. So one of the upshots for this is that so turbulence is actually fundamentally hard. It's fundamentally hard because it's really not Gaussian. So it's not just random white noise kind of fluctuations we're dealing with. It's really red. And in particular, the nonlinear transfer of stuff really do matter. So most of these kind of closures have some sort of skill in one aspect, but they are, I think all of them are ultimately something, all of them are ultimately incorrect. They do something not physically correct. All right. From a modeling point of view, in some ways you don't really care, but like from an understanding point of view, you kind of care about these things. Right? Just to point out a factor, so really it's to do with this what's called a factails problem. So if you're taking a PDF of the fluctuations, you have really factails. So physically, what these means is you get the kind of existence of these near singular structures. So these near singular structures occur with small probabilities, small but not negligible probabilities. So what that means is you really do care about these things, because these things can actually end up sweeping and affecting your kind of small scale things. And describing these things is not really a trivial task. But I left this up because it turns out that, so this paper has actually been on my reading list for the past few years. I haven't read it yet. So it takes a what's called instanton approach. So this actually turns out to have some links with quantum field theory and Yang-Mills theory. So Yang-Mills theory, for those of you who do these kind of stuff, there's an approach where you construct what's called instantons, and then you average over instanton gas to give you essentially that ends up as a way to sample your factails, your kind of small probability but important effect. So that's kind of interesting in some way. At least for me, it was interesting, right? But so one is quantum field theory, and the other one really is classical mechanics. On the first sight, you might think, well, they have nothing to do with each other. So why would something be this? Some sort of commonality between those two. And again, maybe the way you want to think of this is that really we're dealing with strongly interacting nonlinear multi-scale systems. All right. So in that sense, like tools developed to tackle things in QFT might actually have applications within kind of the classical fluid mechanics case and kind of vice versa. One example, so another example which I know of is I think people look at wave turbulence, so turbulence of waves using a path integral type approach. So this is actually from Hasselmann in the 70s or 80s. So Hasselmann was the one who won the Nobel Prize in physics this past year. So he actually does a lot of these kind of things as well. So I'm just going to leave that there. So closure, the statistical kind of approach doesn't really work for the Navier-Stokes. So let's go even more basic. So let's suppose you just brute force it. So the question I'm going to ask here is how much resource do you need? So how much computer power do you need to throw at simulating Navier-Stokes? So I'm going to essentially take what's called a direct numerical simulation approach, or DNS approach. So what I'm doing is so given the scale, I'm resolving all the big scales all the way down to some sort of small scales. So the question here, what is the small scale? So the bottleneck turns out will be the small scale. Okay, so in the Navier-Stokes problem, if you non-dimensionalize it, so that's how usually a sensible thing to do. You want to non-dimensionalize it to get the key parameter. But it's not the individual parameters you care about, it's a combination of parameters you usually care about. The most fundamental one is really the Reynolds number. So the Reynolds number is some sort of velocity scale, length scale over this is the kinematic viscosity, so it's a measure of viscosity. So the upshot here is that a small Reynolds number means viscosity is important, and large Reynolds number means the effective and then inertia terms are important. And the dynamics really are dependent on the Reynolds number. So if you're dealing with things like bacteria, it's a small Reynolds number. But if you're dealing with fairly generic, sensible things, then these usually have a large Reynolds number. Okay, so the argument I'm going to give is that the constraint on computer resources would be on the smallest length scale you have, so this kind of smallest length scale. From a spatial point of view, because you want to discretize such that you want to give enough grid points to resolve these small scale fluctuations. Usually, the small scale fluctuations have associated with the fastest time fluctuations. So from a numerical stability point of view, you want to also have a small time step. So it's really the small scales that dominate everything. That's really the deciding factor on how much resource we need. So we want to get a theory on, well, what is the smallest length scale? And particularly, how is it related to the Reynolds number? So this one I'm going to very skimply on. So there's a theory called the Kolmogorov theory, which dates back to 1941. You have to make a whole load of assumptions, but if you take those assumptions, you can essentially do dimensional analysis. And what you find is that the energy spectrum in spectral space, K the wave number. So energy spectrum has to go like K to the -5/3 away from some sort of, away from the forcing and the dissipative scaled. So if you put this in a log graph, what that's telling you is that this thing has some sort of constant slope. Statistically, it has to have some sort of constant slope. From this theory, what it tells you is that there's this thing called a Kolmogorov microscale, where you assume that everything beyond that gets killed off by viscosity. So from this theory, it tells you that this Kolmogorov microscale goes like Reynolds to the 3/4. All right. This thing in particular assumes that there's what's called a local cascade. So somehow you have these big eddies and they're splitting the smaller ones and then the smaller ones and the smaller ones. They do these by steps and they don't do it from a continuous way. Or rather the kind of things which are occurring, which are forbidden or somewhat kind of occurring with very low probability is a big stuff immediately going to the small stuff. So here you're jumping from here all the way down to the bottom bits. That has a low probability. It turns out that's not true, but it actually does. It modifies it somewhat. And, the bulk cake with -5/3 doesn't really get affected. So the key point here is the Reynolds to the 3/4. Right. Then you can kind of see what's going to happen, right? So the thing I'm going to ask is that, so how many points do you have given the Reynolds number? So once I choose my Reynolds number, how many points do I need? And how many operations do I need to run this calculation? In the 3-dimensional case, you take Reynolds to the 3/4 cubed, so it's Reynolds to 9/4. The number of operations is really 3 + 1, right? So it's three spatial dimensions and 1 in time. It's because of the time stepping. So what you're going to have is going to have Reynolds cube scaling. So you can kind of see what's going to happen, right? My Reynolds number is going to be large, so my N and M are going to be massive. So I'm going to give you 2 worked out examples. If you take a kind of reasonable Reynolds number of 10 to the 10, so this would be kind of reasonable for geophysical and astrophysical applications. What you would need is if you were to store each point in double position, so that's 8 bytes per point, you need 10 to the 11 terabytes for one 3-dimensional variable. So just for reference, so a standard computer like this one, the one I'm using, has memory, so a hard disk memory of 1 terabyte. So there's a 10 to the 11 difference between these things. Okay, these are not just 1 or 2 orders of magnitude; these are like tens of orders of magnitude difference. A national level supercomputer would, I think it's still probably around a petaflop. So this is 10 to the 15 operations per second. So the time required to do these things is it's 10 to the 30 divided by 10 to the 15, so it's 10 to the 15. So I make that 300 million years per time step, by the way. This is not just, you know, for the simulation itself, it's per time step, probably. And you're going to, so the problem is going to be, if you change it by factors of 2, you're not really dealing with this problem, right? So we're not talking about, you know, when we do simulations, you want it on the order of weeks or maybe months. You don't want it years, let alone millions of years. So what that means is that when we want to explore Reynolds number dependence, we're very limited to what we can do. Even 10 to the 6 is actually quite hard. If you use a slightly different theory, so if you use what's called the Taylor microscale, you save it a little bit, but not very much. You still get things like the quadratic scaling. So that's kind of the issue with computation in Navier-Stokes or fluid turbulence problems, is because the scaling is really bad. You get at least a quadratic scaling, so things blow up really fast. Okay, so I'm just going to leave this kind of conclusion for the first part over. I've gone way too slow on this one. So turbulence is hard because Navier-Stokes is hard. And now the mathematical analysis is very difficult. So we have no conditions really we have very few conditions as to say when Navier-Stokes will behave, and we have even fewer conditions as to when it doesn't behave. We just don't know. So in the absence of knowing the right thing to do, you want to know at least how it blows up, right? We don't even know that. From a description point of view, from a statistics point of view, it's very difficult to describe these things because you have the closure problem in the infinite hierarchy. Most attempts at some sort of closure doesn't really work. There is some sort of fundamental limitation with these things. From a computation, we can't just throw computer power at it because the scaling is so bad. You're going to basically kill your computer. So what that means is that it's just hard. There are some ultimate limitations, but it doesn't mean you give up and go home and cry. Otherwise, you know, there would be the research field would be dead. There are certain things that you can still do, and that's usually kind of one of the things I would recommend for postgrads, particularly going into research, is really trying to think of a way to simplify your problems somewhat. I mean, don't go tackling head-on to a really hard problem. Maybe think about what kind of easier problems you can do to chip away at the larger problem as well. Something related or something kind of something either related or something directly or tangentially related is always a good thing. So the two things I'm going to be talking a little bit about is to do with kind of two limits. I'm going to talk about the really viscous limit and the ideal limit. So I'm going to talk about the really viscous limit first. So here I'm really thinking of low Reynolds number flows. So one of the things you find with low Reynolds number flows is it gives you a very strong constraint on what's called time reversibility. So a lot of things end up being time reversible. So the example we're going to, the video I'm showing here is using what's called a Taylor-Couette flow. So you have a concentric cylinder, and what you're going to do is you drive the cylinder, and it's going to drive a boundary-driven flow. I'm going to skip forward a little bit. So what he's going to be putting in is some sort of really viscous fluid. So in this case, I think it's glycerin he's going to put in. So here he put the glycerin in, and he's driving a flow essentially. What he's going to then do is going to put some dye into this, inject some dye, and he's going to start driving a flow. Right. As you start turning the cylinder, it's going to end up smearing the thing out. So he's going to do it fairly slowly to keep the Reynolds number slow, kind of low. Right? He's going to do it a few times, and what you find eventually is going to start mixing up. So you get these bands of stuff which is mixed. So this is a fairly classical experiment. What he's going to do is going to reverse it. And what you find is as you reverse it, it actually unmixes. So it looks like on the surface it's actually mixing, but there is actually no mixing going on. Because in this case, the flow is somewhat time reversible. So for time reasons, I'm going to skip forward a little bit. So he's going to turn back to this one. Let me take a swig. Okay, so that's what you end up getting. So there's a bit of smearing out, I mean, that's inevitable. But the bulk of it hasn't happened yet. So this doesn't happen in very non-viscous fluids. So the example would be if you have a cup of coffee, throw a bit of milk in it, it just diffuses really quickly. All right. So the main point here is that the low Reynolds number gives you a very strong constraint on time reversibility. So the context I'm going to give it here is for micro swimmers or small swimmers. If you're a small kind of a dinoflagellate or some kind of small microorganism swimming in the sea, for example, so remember the Reynolds number is UL over nu. So even though the viscosity is not very low, if your flow is low and your length scale is low, then the Reynolds number is going to be low. So for small swimmers, you are subject to the low Reynolds number dynamics. Then what that might imply is you can't get this swimming going on, right? So one thing you can do is actually formalize this properly in what's called the scalar theorem. So I put this in because I like the scalar theorem. It's to do with scalars. I'll demonstrate what that actually does. So imagine you're a scalar. What you're doing is, if you want to propel this way, you close your lid and you push the flow out and you move a little bit, right? But in order to do that again, what you need to do is you need to open. But when you open, you're pushing fluid back. Then you go back to where you started off with. So what you're going to get is you're just going to get something like this in a really low Reynolds number flow. Okay? It doesn't matter how slow you push it, because you're always essentially in a low Reynolds number regime pushing against something. So you can formalize this properly. So what this is saying is that, so technically really it's for Stokes flow. So Stokes flow is where you throw away the ddt term and the inertia term. So in the Stokes flow case, what you have is that time symmetric motion with, in this case, with only a single degree of freedom gives you no net motion. So scalar can't propagate in this kind of regime, right? But obviously things do swim. So just to give myself a break, anyone like to have any advances on what you can do to get away from the mathematical theorem called the scalar theorem? So how do things actually swim? So what could you do to like break this kind of constraint? You can just type in the chat or anyone likes to try giving an answer with it. Oops. I'm giving you a hint here. Well, for time reasons, I guess I'll move on. It's to do with time symmetry. You just break the time symmetry, right? So you just don't do this. So one thing you could do is you do this. You swirl around. So that's what actually a lot of microorganisms do. So here, this is a paper taken from a review paper led by Julian Mak at Oxford Physics, I think. So this is these are some pictures of kind of microorganisms and how they microorganisms. So this is sperm, I think. Panel A is sperm. So what you do is you just whip it around. So you end up driving you do it in a helical way. So if you're doing it from a helical way, you break the time symmetry. So you introduce some sort of chirality into it. So that gives you some sort of propagation. The other one, sometimes with these with kind of tentacles, they do what kind of whipping motion. So when you whip the thing, so that the dynamics of how whip works is that the thing travels at the end travels much faster than the other side. It's like a swung pendulum, a slack pendulum. So what that means is that when it whips out the thing, you end up breaking the small Reynolds number condition because it's traveling sufficiently fast. What that usually means is you can generate some sort of vortex, and that vortex gives you some sort of propulsion. So that's, for example, how jellyfish swim. So when jellyfish push it together, they end up giving you a pair of vortex, and that gives them the propulsion. So these kind of things are actually, so another way you can do this is you can swim in a collective. If you're in a collective, that doesn't really, in some sense, that doesn't necessarily apply. Another way is you look at what's called complex fluids. So in my case, I consider Hamiltonian fluids, but if you consider things like shear thinning fluids and other kind of weird and wonderful stuff, you can actually break this constraint as well. This is a really active area of research in biological physics and soft matter, actually. It's because it's got some sort of physiological applications. So I'm going to leave it at that. So related to that, I'm going to go into the other extremes. So that's to do with the whipping thing, generating the vortex. I'm going to take a digression using to kind of standard aerodynamics. So the whipping thing is actually related to aerodynamics as well. So the main point here is that if you want things to fly, you need some sort of lift to counteract the weight. Otherwise, so that's everywhere anyway. You want something pushing it up. So the classical way of attacking this is you consider the extreme opposite. So what you do is you say, okay, let's take the Reynolds number infinity case. So you have no viscosity whatsoever. And then if you do a change of frame, because the Navier-Stokes equation is Galilean invariant, so you can just change the frame. So instead of a thing flying through a fluid, you have a fixed thing and the fluid is moving past the obstacle. So you turn it into a problem of flow past the obstacle. In this particular case, when you're in physics, that has a very strong constraint. So you end up, if you have a uniform flow past an obstacle, initial uniform flow coming in, that would be irrotational. So there's no curl. And in this particular case, you're constrained to not be able to generate any curl. There is no vorticity that you can generate in these cases because it's in physics. Incompressible just comes from the fact that this is, you have to conserve mass in this case. So if you are curl-free, if you remember from your either vector calculus or electromagnetism, you can introduce a potential. If you are diff-free, so you have no divergence, you can introduce what's called stream function. So what you have is you've got a velocity to describe a potential and a stream function with a grad curl. So this is like, so think of it as like a grad operator rotated 90 degrees. If you put it this way, so I've actually given you the punchline here. So this actually is the Cauchy-Riemann equations, if you know what that is. So if you've done kind of basic courses in complex numbers, then you would probably have encountered this before. So what that means is, in this case, is that if the phi and psi are solutions of this thing, so which is what you want, you can construct a W, which is an analytical function. So there's a theorem in complex analysis which tells you that if these are solutions of the Cauchy-Riemann equations, then W is analytic. So this is an only if statement. All right. Then what you can do, so that's the kind of usual trick in complex analysis when you're dealing with potential flow. So what you do is you have your W for a circle. So you want it for a certain configuration. So in this case, it turns out you can actually get an analytical solution for the circle. So both of these end up being Laplace equations. You can solve it with a subject to a boundary. You know the W from this. Then, because W is analytic, you can do things like conformal mapping to it. So you can map it to other solutions. So a particularly famous one is called the Joukowsky transform. So the Joukowsky transform, if I remember right, is I think it's Z equals W plus 1 over W. So you can show that that is a conformal mapping. So you can map so if you know the solution to flow past a cylinder, you know the solution to flow past the aerofoil as well. So what's called Joukowsky aerofoil. So that's how I actually learned it in the first place. So I had to take a compulsory course in complex analysis. So I mostly, before I took a fluid dynamics course, so that's actually how I learned about these things initially. So the upshot in this case is that there is, however, no drag and there's no lift. So the fact that there's no drag is not entirely surprising in some sense, if you think about it, because there's no viscosity, right? So there's nothing dragging anything. The more problematic thing is no lift. So in an ideal fluid, you cannot get any lift. So the way you think about it is that there's nothing being pressed against. The aerofoil has nothing to press against in an appropriate frame of reference. So you cannot get a reaction coming out of it. So this is an example, kind of fairly classical example of a singular limit in these kind of fluid equations. So in the real world, you don't have infinite Reynolds number. You have large but finite finite Reynolds number. So in the infinite Reynolds number case, you have the irrotational constraint, which means you cannot generate any vorticity. And you break that with introduction of what's called boundary layer. So what you do is you solve the solution away from the obstacle, but you say that within the very close to the obstacle there is a solution where there is a part where your solution is viscosity dominated, and you match the two solutions. So if you have finite Reynolds number, then you are allowed to break the irrotational constraint. What that leads to is some sort of vortex. So generation of vortex then leads to some sort of non-local flow. And that is the thing that actually ends up contributing to lift. So what you have is you have an aerofoil, and that shreds off a vortex, and that actually shreds off another one. So it's this thing which actually ends up contributing to giving you the lift. All right. So there's a standard example which is calling, was it the Cut principle equal transit time? You end up driving a pressure. That's not true. That's not how it works. It's really to do with the fact that you have a vortex coming in. So this is a bit like the Barlow law, if you again from electromagnetism. If you remember, if you have a wire, you have a current going through it, you have a non-local magnetic field. So in this case, what you have is you have a localized vortex, localized kind of line vortex, and that generates a non-local flow, and that's the thing that ends up giving you the lift. So what that ends up leading to is that the key role of vortices and gives you some understanding of what's going on. You might want to then further take this further to understand boundary layer turbulence, how the vortex is generated, etc. From an engineering point of view, mathematical point of view as well, you might be thinking it'd be interested in things like optimization and control problems. So how to design error for various objects to minimize or maximize certain things. Okay. So these have got applications in designing kind of robots, so particularly flapping wing robots. So flapping wing robots have much more maneuverability than I guess standard things with fixed wings. So these are like drones essentially. And also if you're interested in understanding how insects fly, because these things, it turns out so it turns out that one of the most important things is actually the role of the vortices in these kind of cases. In certain cases, we can actually solve this. So this is a particular example which is called topology, a topological vortex. So it's topology breaking, which leads to vortex generation. So what you have here usually is like when you swing a breaststroke. Imagine your bee. So your bee comes in the wing. It comes in, it puts it together, and then it breaks it. So this is, you would regard this as like the whole domain would be a singular connected domain, possibly with a branch cut. And then when you break it, you end up having two branch cuts, and this is changing the topology of the system. It turns out these kind of things you can actually still solve using the standard potential theory approaches. So I left this as a mathematically interesting example. You can look at the paper by Kolominsky al. For this kind of thing. Just a shout out actually to our HKUSD outgoing president. So this diagram is from Wei-Shi's book on the introduction to flapping wing dynamics, aerodynamics. So that's actually what he does. So he's a mechanical engineer. He's particularly focused on how aerodynamics of these flapping wings with a view to build robots for these stuff. Okay, then you can start doing weird and wonderful things. So one thing is you can do like simulations. You can say, well, what's the aerodynamics of a cow? Because why wouldn't you want to know about aerodynamics of a cow? I don't know. The right-hand side one is actually more interesting. I thought it was a joke actually. So it's aerodynamics of Pringles. So the idea here is you want to maximize the production of Pringles. So when you have Pringles on a conveyor belt, so what you really want to do is you want to maximize the speed the conveyor belt goes at. But if you go too fast, then that ends up generating a lift, and that can end up lifting off Pringles. The Pringles are not very heavy. So what you might want to do is you want to do some calculation to say, how do you optimize and control the conveyor belt speed accordingly to minimize the probability of these things dropping off. So I thought this was a joke, but I actually looked up Procter & Gamble. So Procter & Gamble is the parent company of Pringles. They are one of the very few multinational companies that are very open about how they use high-performance computing. So you can actually look in there. There's another example which is to do coffee beans, which is actually I thought is quite interesting. Another example you could do, so this is a recent paper in GFM Rapids, 2021. It's about ducks swimming. So this is slightly different to the geese problem, or the flying geese problem, or the the bikers problem. So as you know, geese tend to fly in a V formation because of you end up being in the wake. Well, you end up not being in the wake, you end up getting some sort of shielding effect. And similarly, when you are biking, so when you see Olympic bikers, for example, they then try and get as close to each other as possible within a team. This is slightly different. This is actually, because this is on an interface, so it really is to do with waves. So this is a free surface of sorts. And what they found is they calculated that if you want, there's a certain optimal position. So if you have a flow path cylinder, you know what kind of waves it generates. There's an optimal position where you end up riding the waves. So you have some sort of, you end up riding the waves rather than being in some sort of destructive interference here. So this one would expend more energy than the one on top. So this is actually quite an old problem which has recently been quantified properly. These kind of things have applications in things like, I suppose, wind turbine placement in wind farms, say. Also kind of optimization problems within the kind of structure design, kind of naval structure design. So these people are kind of naval engineers, for example. All right. Okay, so this next bit I'm going to skip. It's to do with chaotic mixing. The only reason I want to put this in was to put this picture in. But so it's to do with braiding. So it turns out chaotic mixing, you think of it as a braiding problem. Braiding problem, it turns out, also has links with group theory. For those of you who are interested in string theory, braiding ends up inducing topology. So sometimes one of the things of interest is actually understanding how do these things end up, what kind of topology certain strings have. And you can actually boil these down to some sort of braiding type problem. You can attack these using some kind of group theory type arguments. I'm just going to leave that. Okay, so maybe give me another 10 minutes or so. I'm sorry for overrunning here. So I'm going to talk a little bit, very quickly, talk a little bit about the things which I've been dealing with. It's really to do, so it's motivated largely by shear instabilities. So this is from my PhD. So it's like what happens when you have a shear flow that goes unstable and you have a magnetic field. So one of the interests here is what's actually going on. So how do these things go unstable? So how do you describe the things going unstable? So I'm going to talk very quickly, fly through these three topics, and the unifying kind of there's a unifying theme between all of these symmetries. So all of these have some sort of role. The symmetries have a very strong role in these. Okay, so when we talk about stability, this is the kind of example you might think of. So you have a kind of object and you kick it at some equilibrium and you kick it a bit. Question you ask is, once you kick it a bit, how big does the perturbation grow? How does it decay? So if it decays, then you think it's stable, and if it grows, then you call it unstable. The problem here is that it doesn't matter which direction you're kicking the thing in. And what do you mean really by large? So when you say you have a perturbation getting to be large, what do you really mean? Sometimes this could be energy, sometimes this could be displacement, it could be a whole load of other stuff. One of the questions we're interested in here is how do you derive these stability conditions? In the fluid case, it's actually exacerbated by the fact that fluid systems you really regard as an infinite dimensional system. So in a finite dimensional system, you only need to check the finite dimensions, right? Infinite case, you have to, if you want to show stability, you have to check every single infinite amount of these directions. In the infinite case, the norms are not equivalent. So what you measure as big depends on what you decide, what your measure is. So in finite dimensions, that's not true. In infinite dimensions, that is true. There is a non-dependency here. So when you talk about stability, you have to talk about what do you mean by large. And then there's some conditions to linear and non-linear condition. How do you get these kind of stability things? So in stability, in a way, it's easy. Right? You just kick it and see if it grows. If you find one direction it grows, then it's unstable. Stability is much more difficult because you need to show everything is unstable. Everything is stable, regardless of how you kick it. So the standard way of doing this is there's this what's called energy type method. So here you assume you try and essentially bound the perturbation in terms of some sort of energies or L2 norm, or if you like Hilbert spaces, this is the L2 norm is is one of the things which induces some sort of completeness in the Hilbert space. Doesn't really matter. I'm not going to touch that. So these kind of methods essentially are restricted to what's called self-adjoint operators or Hermitian operators. So the idea here is in a Hermitian operator or self-adjoint operator is a Stern-Liouville problem. So that's the kind of standard things you do in quantum mechanics. You have a discrete spectrum and you do a variational problem and bound the bottom. So essentially you say there's a variational inequality. You say everything can be bounded by the eigenvalue. This only works for self-adjoint operators. For the kind of stuff I'm looking into, which is shear flows, it doesn't work because it's ultimately it's non-Hermitian. But what you can do is construct some sort of energy-like quantity to serve as a norm, but you have to be a little bit clever about these things. Then you can proceed as usual. You take essentially a first and second derivative. So the first derivative tells you where there's a critical point, and the second derivative tells you where there's a local maximum or minimum. So if it's a local minimum, then you're good, essentially. But you have to be a bit clever about constructing these. So one way of actually there's an algorithm which lets you construct these properly is using the Hamiltonian formulation. So the idea here is the Hamiltonian has a link with the Fourier-Legendre transform has a link with Lagrangian. So you can mimic it. So in this case, you can leverage the leverage Noether's theorem. So if you can find a symmetry, then that has using the symmetries in the system, you can explicitly construct the conserved quantities. All right, and you can use these then to construct the norms, and then in turn you can talk about, okay, if I do a variational problem across these things, can I at least get some sort of stability condition out of it? They have other uses, such as you get what's called non-acceleration theorems, which is important for understanding how the small scale feedbacks on the large scales. So the idea here is you have a Hamiltonian, and you construct what's called a symplectic operator, which is J here. So all the symmetries are nested here, essentially. In the canonical form, this J is just what, 0, 1 minus 1, 0, or something like that. So in general, this is not, J is going to be something more complicated. There's several ways you can deal with this. So you can either, so you can get a canonical form by introducing what's called Clebsch variables, but let's not do that, but that's pretty ugly. So I much prefer doing it from thinking of it from a symplectic operator point of view. And the non-canonical form comes from the fact that you're dealing with fluid or Eulerian state variables. Right? And all the symmetries are nested in J. So, so that turns into a problem analyzing J, this symplectic operator. In particular, there's a special class called Casimir invariants in J. So these are the invariants which are nested in the kernel of J. The suggestion normally is you combine these Casimir invariants with other invariants as a way to construct essentially your quadratic forms as which then you ask, can you use these quadratic forms to generate, to use this as a measure of a perturbation. These are essentially actions, okay? So you can combine it with Hamiltonian, give you a pseudo energy. So this is time symmetry of the Casimir invariants, or you can look at translational symmetries, which gives you momentum and momentum with the Casimir. So this gives an algorithm deriving these conserved properties, which in turn have other uses, kind of deriving stability conditions and so forth. All right, so that's one of them. Quickly fly for the next two. The issue of topological protection. So if you know condensed matter, in the condensed matter literature, what you have is these topological insulators. So separately, you have two materials that are very good insulators, but somehow when you put them together, some of them can be very good conductors on the edge. So this ends up what's called a bulk boundary correspondent. So the bulk from the bulk properties of the two things, you can actually get at what's going on on the edge. So the idea here is like what you have is you put the two things together, then the wave function has to transition from one to the other one, but it's topologically distinct, so it's really difficult to transition. So what that means is you end up generating extra edge mode, which gives you the transition. That also turns out to work in the rotating system. So what you can think of is so here you have a northern hemisphere, southern hemisphere. Individually, these have certain wave properties, and it turns out certain wave types have a topological characterization, in this case in the spectral space. And if you put the two together, then depending on the topology of the two, then you necessarily have to introduce extra edge modes. In the geophysical case, this is known as a Kelvin wave and a Yannai wave. So it turns out in this case, the Chern number jumps by 2, so you have to get 2 modes. So that's the Kelvin and Yannai wave. So these things have applications in climate. So particularly Kelvin wave has a strong application in at the El Nino signals. So this is an example of El Nino. So the Kelvin wave is important because it ends up propagating signals from the west to the east. So that's why, in some ways, then you can ask, so these are presumably persistent features because of the symmetry protection. How do they behave in the presence of shear, and what kind of role do they have in climate and large scale simulation and so forth? So that's something I recently picked up. Last one before I stop. So in quantum mechanics, normally you deal with permission operators. So these are the Salvage-Join operators. Partly because you have a real spectrum of real observables. So the question you might be asking here in this case is that do you really need to have a Hermitian operator to get the real spectrum? The answer is no. So this has actually been advanced by a lot of work by Carl Bender and collaborators. If you have a non-Hermitian but PT symmetric operator, the PT is parity in time. Those can have real spectrums, and usually you can use these as modeling things like loss gain systems. So they have particular applications in optics and also in optics and lasers and so forth. So this is a particularly good book. I highly recommend it if you're interested in this kind of topic. dimension in shear flows here, essentially what you have is some sort of PD symmetric system. So you have it turns out you have a non-Hermitian but PD symmetric operator. So the idea here being that the kind of things which are used in quantum mechanics can be used that to leverage to understand how shear instabilities work, or how classical PD system symmetric systems work. In particular, my main focus is on wave propagation. So there's a kind of understanding that the shear instabilities arise from an interaction of two waves. So how does PD symmetry play a role in these kind of wave propagations and in the wave interactions and so forth? Is it that PD symmetry gives you, the breaking of PD symmetry, is that a necessary and sufficient condition for stability? Or is it just one of them? So these are kind of conjectures I've been kind of thinking about a little bit on my kind of spare time. But I leave that out just as kind of open kind of conjectures. All right, so that's basically it from me. So just a few more kind of tidbits. I'm not going to talk about these very much because I've run out of time already. There's some other non-trivial links with fluid systems with other things. So fluid systems, for example, has applications in plasma physics, or these are mathematical analogies for plasma physics. So there's something called the Hasegawa-Mima equations and what's called the quasi-geostrophic equations in the rapidly rotating case. They have a mathematical form of similarity. So this is coming from the fact that both of them can be regarded as rapidly rotating in some sense. In quantum systems, actually, this is fairly well known. I don't know if it's well known to you, but apparently it's well known. You can take what's called the Madelung transform of Schrodinger equation and turn it into essentially the 1D ideal compressible equations. So this dates back to Madelung in 1927. The suggestion here, maybe if you understand the ideal compressible equations, I can tell you a little bit about a Schrodinger equation. This one, don't ask me this because I don't understand this one. So there is a link with generativity, apparently. So the P+1 incompressible Navier-Stokes solution has a duality with P+2 vacuum Einstein equations, apparently. So this is written in this paper by Irene Bredberg and collaborators. So this is an example of a holographic principle. So in some sense, you can think of this as like some sort of the Navier-Stokes solution as some sort of boundary to the Einstein equations. Einstein solutions of the boundary solutions of the Einstein equations. So I put this up here because this is a bit like the for those of you who deal with quantum mechanics. So this is the ADS, a bit like the ADS-CFT correspondence. So the ADS is something to do with cosmology, and CFT is quantum field theory. So there are various. So these are actually kind of well studied, and there are lots of active research into these kind of principles. So arguably, maybe there is actually also some link with the from a fluid dynamics point of view with quantum mechanics. Maybe I'm just going to leave that out as a possibility here. There are other approaches which I'm going to skip. So this is related to some of the work I do to do closure problems. So one of the things which I've been working a little bit on is on, so suppose you propose closures, maybe you want to propose closures in such a way you preserve the underlying symmetries of the problem. So that's something which I've been dealing with a little bit. Something else I've been looking into is machine learning. So how do you do machine learning? So in the closure, maybe you understand closures. How do you do physically constrained machine learning? In this case, preserve the underlying conservation laws and possibly the underlying symmetries of the problem. Again, maybe the upshot of this is that if you take care to preserve the symmetries, you take care of preserving your conservation laws. And conservation laws are always a good thing in physics. Okay, so with that in mind, there are also other possibilities of looking at other fluids. So I'm just going to leave this out here. You can question me about it later on if you want. So I talked too much, so I'm going to stop here. Thanks for your attention. Sorry for running over time. I'm happy to take questions and just have a chat generally. All right. That's me done. So if anyone likes to ask any questions, you're welcome to. Tough crowd, quiet crowd.
I would like to know.
Yeah.
How the existence of the magnetic field affects this energy cascades in the flow?
Right. Yes. Let So it's this stuff. So I'm going to leave an interesting photo, animation as a distraction here. So that the bottom animation I made is it was called it's like LES. In the presence of a magnetic field is a little bit more touchy. So if you're interested, so this is based on the Kolmogorov theory of local cascades and so forth. So that's been extended somewhat to include MHD. So you can use a similar argument in MHD. This is, I think, still somewhat being debated. So this one of the first theories to do with this is the Krigman-Eroshnikov theory. So that tells you have k to the -3 halves, but there's an inverse cascade. So the reason for the inverse cascade is that you end up breaking some of the symmetries within the, so the magnetic field ends up breaking some of the conservation laws within the, particularly to do with the vorticity stuff. So you can essentially do a similar argument, dimension argument to get that. Another one is the Goldreich and Schritt-Haar. I think that's in the 90s. So that gives you k to the -5/3, but in the, sorry, it's k to the minus, so Krigman-Eroshnikov is k to the -3 halves, I think, but downscale. The magnetic field, so the Goldreich Schritt-Haar, I think, gives you k to the -5/3, but in the perpendicular direction. So it gives you some sort of anisotropy. So that's one of the things that the background magnetic field introduces, some sort of anisotropy. So the standard Kolmogorov theory doesn't work, right? Because it assumes that there's some sort of anisotropy in there. Another piece of work I know, it goes back to, I think, Stanislav Brodiev, that's I think in the mid-2000s into the mid-2000s to mid-2010s. So they've been looking into how you actually merge the two theories. So how do you transition from the Krigman theory to the Goldreich Schritt-Haar theory? So if you want to chase up some stuff there, so the key role is the anisotropy. So magnetic field introduces some sort of anisotropy in there, makes the analysis a little bit more difficult. But that is research in MHD turbulence, because that has implications for things like dynamo as well.
Sorry, I don't understand what is happening in the video, at least in the middle side. What is being introduced? Are there some repelling force between the edges?
Sorry, say that again.
I'm sorry, what is happening in the middle of the video?
Oh, this video. So this video is a ocean simulations out of ridge. So this is, so here what you have is what's called potential vorticity conservation. So this is actually related to Casimir invariance. What you have is that potential vorticity, so this is angular momentum conservation actually. So this is an ocean where you have, it's what's called beta plane. So your thing rotates faster here than it is, sorry, Coriolis force is stronger at the poles than at the equator, which is in the north. For angular momentum conservation, because of the ridge, as your flow goes into the ridge, it has to go up. But it has to go up in a way which conserves angular momentum. So it has to go up in this case, and it has an equatorward deflection. So what this is telling you is that there's some sort of shielding effect going on here, just by the presence of a ridge. The whole depth is 4,000 meters, but the ridge only goes down to 2,000 meters. So even though there is no actual physical, it's not a physical wall itself, but it acts as if there is a physical wall blocking it because of the, in this case, because of angular momentum conservation. So that's what this video is about. And these are the kind of things you can do with fluid dynamics. You generate really nice videos. So that's partly why I kind of look into these things.
I see. Thanks for the explanation.
I mean, quite proud.
Great talk, by the way. But I have maybe a stupid, maybe I'm missing something. I just want to know how to quick answer how to quantify the linear instability inside vortex.
Linear instability. So can you say that bit again?
How to quantify linear instability in turbulence?
Well, okay. So the thing you would want to do first is to consider a slightly simpler problem. So what you do usually flow. So you just choose, you find a solution of the, for example, let's go back to here. So it's like how you deal with a pendulum. I think it's kind of similar. Or like if you do analysis of things like the Van der Waals type equation. So what you do is you take a dynamical system, you find equilibrium points of this. So one equilibrium point of this would be 0, right? So if I take 0, then as long as I'm like some sort of pressure balance, then it's good. So if in this 0 case, one thing I might do is I might set up a unstable thermal driving. So this would be like in the convection case. Now, what you would ask is that suppose I kick this 0 a little bit. So how does my perturbation form given the unstable stratification? So usually what you do is when we talk about linear stability, you look at it from a really simple point of view. You give it kind of prototypical instability, prototypical basic states, and you perturb over it. You're linearizing, you say you try and get rid of something which is the non-linear term. So you turn it into a linear ODE or PDE. Well, linear ODE usually, particularly if you take Fourier analysis. So a first order linear ODE is always solvable, unless the boundary condition, unless the ability to initial value problem, essentially. So that's studying from a dynamics point of view, that's what you would do. If you're starting to talk about linearizing against a turbulent flow, that is a little bit more kind of suspect, and it's actually quite difficult. With that, we don't really know what to do in some ways or another. There's certain cases where you can deal with it. For example, if you have a periodic, if you have a time periodic flow, then you can do things like flow K analysis on it. But if you're really talking about a general turbulent flow, you have to either make some sort of assumption that within the time you're doing a linear stability analysis, that your background state is not changing very much. But that's really the problem. When you're linearizing, it only works for essentially infinitesimal time. But if your flow is constantly evolving, then it's, when you're trying to linearize things, it's a little bit more suspect. There are ways which you can consider things like generalized stability theories, I suppose. So you ask, okay, how does the perturbation grow in time from a general point of view rather than a modal point of view? But that usually is more numerical as well. So in general, you can't really do it. In special cases, you can.
Thank you. Nice talk, by the way.
Great, thank you. I've blown everybody's minds, that's probably why. All right.
I still have a question about the numerical side. So in order to calculate the Navier-Stokes equation and simulate the eddies numerically, we have to define the grid size carefully. But no matter how small we define the grid size, the eddies can always go below. The dynamics of eddies can always go below the size of the grid.
That's right. Yeah.
That's right. So actually,
yeah.
how large the effect is that, and technically, what kind of techniques can be used to deal with this kind of problem?
Okay, so that's to do with the closure problem. Let me go to the relevant slide. So it will be here, probably something like this, I guess. So this is a balance between practical and physical stuff. So theoretically, you know how. So given a Reynolds number you want to simulate, you know exactly roughly speaking what's the smallest length scale. But of course, as I highlighted there, you are also limited from a practical point of view, from a resource point of view. So one thing you can do, so from a practical point of view, one thing you might say, you might flip the question around to say, okay, how much resource do I have? So given that amount of resource, what is the smallest length scale I'm allowed to resolve? So you kind of flip the question around, and what you do is you just artificially you study the problem in a different regime. Usually, if you do that, then you are no longer working in the large, you're no longer working on the, so your Reynolds number will be different. But that I think is not, how should I say it? As long as you're not over-claiming to say that if you're simulating, as long as you're not over-claiming to say that whatever you're simulating is some other object, then I think that is okay. So one case, this is an anecdote. So I went to this talk at some point and someone claimed they simulated the sun. And then they got all these gravity waves in the sun and said, okay, very good. And then obviously, so I didn't buy it. And then someone else asked the question, so, well, okay, so what's your Reynolds number? Blah, 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 didn't answer the question. And then he was like, well, no, seriously, what is your Reynolds number? And then said some other stuff that really also didn't answer the question. And it didn't let go. So I asked him again, so no, seriously, what is your Reynolds number? And he said 20. And so the thing that I think really pisses people off is when you claim you're solving, when you're really solving a Reynolds number 20 thing, you're claiming it's the sun. If you do that, then that's no good. Don't do that. Just be honest about it, because there is a practical consideration, numeric from a computational resource, what kind of things you can do. So that's for DNS. For LES, there's kind of things to do with LES. So here what you might do is to say, okay, so given your resource size, say what is my grid size? What's the minimum grid size I can go? So this is, suppose I choose it here. So essentially I wipe out all these things. Depending on the context, if you're here, then suppose particularly you believe that that you should be in the Kolmogorov regime, then in some ways you don't need to solve everything, right? You just need to solve, and assuming that you don't have any feedbacks from the small scales to the large scales, then you could just say, let's just chop it up here. Anything which is small scale, then I just have some sort of model which is really turbulent diffusion of sorts. And then it's really turbulent diffusion. Then effectively you change your molecular viscosity is something, but your effective or numerical viscosity is something else. So that's usually how these are done in the LES kind of approaches. You have some sort of eddy turbulent diffusivity, which is dependent on the flow field in some sense or another. This doesn't work, for example, in MHD. This is really dubious in MHD, or in cases where you have inverse cascades. Because if you have inverse cascade, you have things going the other way around. Or in MHD cases, so in terms of, for example, in MHD cases, the small scale feedback does affect the large scale. So this is one of the, so this is actually part of my PhD thesis. How does this work? So the setup, for example, in this one, let me go back to the beginning. Oh, I don't have it. Yeah, let me show the video. So this is a case where you send, it's a standard Kelvin-Helmholtz problem, and the only thing I have here is the magnetic field. There's a background magnetic field, and it's fairly weak. It doesn't really do anything. But the dynamics look substantially different. So what this is saying is that the magnetic field in this case, from a linear point of view, doesn't matter. But once you inform on linear dynamics, it really does matter and affects the macro physics. So for those kind of cases where you think the small scale interaction back into the large scale is important, then if you do things like the enhanced turbulent diffusion, that doesn't really work, right? Because that you're essentially screwing up the interaction between the different parts. And in some sense, that's actually quite difficult to model. So that's something that's also kind of prevalent in oceanography, because we want to model some sort of backscatter of energy, but we don't know how to do it. So you have to really know the context, and I think that's where the theory tells you. You need to know what the theory and know what the limitations are. So you can make an approximation. So anyone can make an approximation. But making an approximation in an intelligent and informed way, that's a separate issue. So that really requires kind of understanding of the theory. So in MHD cases, for example, if you do these kind of large eddy simulations, I would be very careful about this. In some cases, it's okay, but sometimes it's very dubious. Particularly for things like Kelvin-Helmholtz. So one of the things I've done is Kelvin-Helmholtz, it really does matter for Kelvin-Helmholtz. So the thing, just be careful. I think is just be aware that some of the things people might be doing might not actually be. It's really for practical rather than theoretical reasons.
Okay, so approximation is the sense that how much number the eddies within the grid. Can I think of it like this way or other kind of approximation?
So the way normally is you have lots of eddies and you take it in a box, but in the box you don't resolve them. So you say on average, what do these eddies do? So one way you can assume is that they enhance the turbulence because they end up shearing things out. That's not the only thing eddies do, but that's the simplest one you can approximate. So it's basically, I mean, I would say maybe it's a bit rude to say this, but it's basically cheating. But if you're cheating, you want to cheat in a convincing way. So in some sense, everything's approximating, but you want to approximate in a physically constrained and sensible way. So it does depend. It depends. So usually the easiest one to do is just enhance the viscosity. So say, for example, in GNU, you have some sort of flux limiters that essentially adds in some sort of numerical viscosity. So that's really more for stabilizing the thing rather than necessarily simulating these software scales. So it kind of depends on what you actually need the things for.
I see. Thanks for the explanation.
Well, people are still hanging around. Okay, if not, then I think I might actually. So now that's going to be on the YouTube. If people want to ask me other questions, are you not comfortable asking here now? So I'll type my email address in the chat box. You're welcome to contact me accordingly. If you want to talk about research or like how have other interesting tidbits in your research field that you think might be applicable to fluid problems, feel free to contact me.